Okay, so I'd like to welcome everybody to another edition of Quantum Computation and Isolation. So I'm very happy to be introducing Professor Earl Campbell today. So Professor Campbell got his master's degree in physics and philosophy from Bristol University in 2005. He was a PhD student from 2005 to 2008 at Oxford University and Simon Benjamin's group. From 2008 to 2010, he was a Royal Commission of 1851 Research Fellow at University College London. From 2010 to 2011, he was a postdoctoral research associate in Jan Izert's group at Potsdam University. And from 2011 to 2014, he was a postdoc at Professor Izert's group at the Free University in Berlin. From 2014 to 2015, he was a postdoc at Peter Koch's group at the University of Sheffield. And then starting in 2015, he was the EPSRC Early Career Research Fellow and lecturer at the University of Sheffield. And starting in 2019, he was a senior research scientist at Riverlane Research Cambridge, and he's currently a senior research scientist in Amazon Web Services Quantum Computing Group. He's the recipient of many awards, including, but not limited to, the Una Goodwin Scholarship at St. Anne's College from 2007 to 2008, the Royal Commission of 1851 Fellowship Award, as I mentioned, from 2008 to 2010, the EPSRC Fellowship Award from 2015 to 2020, and Industrial Collaboration Award from 2017 to 2018. And today he'll be talking about fault-tolerant quantum computing and biased noise architectures. Please help me in welcoming Professor Earl Campbell by either unmuting yourselves and clapping or by clapping virtually.
Thank you. Thank you for the invitation to speak and for the introduction and tour through history for me there. So yeah, today I'm going to be talking about some of the work we've been doing at the AWS Center for Quantum Computing. So the title of this talk is Fault-tolerant quantum computing in biased noise architectures, as you can see. So it's about how we can build a reliable, large-scale quantum computer that takes advantage of bias in noise. So this talk is going to be surveying this very large paper that's nearly 120 pages with a very similar but slightly different title. I guess I chose to have a very slightly different title to emphasize the fact that I'm going to emphasize particular parts of this work more than others. So as you can see, this is a large collaboration involving many people at AWS. And of course, you know, a lot of the work was done by other people and not myself. I won't have time to highlight individual contributions throughout the talk. So there are many different facets to this work, including all the way from the bottom, thinking about what are feasible hardware parameters, then going on to thinking about something called cat codes or cat qubits that I will introduce later on, and the analysis of gates and measurements for those, which includes a lot of perturbation theory and numerics. And this results in some noise biased qubit. But once the qubit is noise biased to be mostly suppressed to bit flips, we still have to correct phase flip errors and possibly some bit flips. So we have to think about error correction. And then we have to think about logic. So we have to think about how to do Toffoli gates. And so there are two different schemes in the paper for how to do Toffoli gates, called bottom up and top down. And then we also discuss application of this to a particular algorithm, in particular Hubbard model, so simulating the Hubbard model. So what I'm going to attempt to do today is an overview of as much of the paper as I possibly can. And so because of the breadth, there's not going to be necessarily a huge amount of depth. It's going to be more of a kind of introductory pedagogical talk. And hopefully, if you're interested in learning more, you can go and have a look at the paper. So the first thing I'm going to cover is noise bias, what I mean by noise bias. So we're mainly going to talk about power noise channels today. You can have other kinds of coherent noise channels, but let's just assume that noise always has some form that looks like rho, the quantum state, is turned into a mixture of the original rho, some amount of X noise weighted by Px, similarly for Y and Z noise. So depolarizing noise, which has no bias whatsoever, is simply the case where all of the three types of noise are equally weighted X, Y, and Z. Dephasing noise, which you might think of as having an infinite Z bias, has no component of Px or Py noise. Hopefully you can see me circling the relevant symbols here with my mouse. If there's a problem and you can't see the mouse, just let me know. Okay, so those noise contributions are 0, but you have some non-zero amount of Z noise. Complementary to that, we can imagine just a pure bit flip noise channel, which has infinite X bias, where you only have some X components. And for both dephasing and pure bit flip noise, you only really need a kind of classical error correction code to tackle that noise, because it's only really classical noise. It's just bit flip, for example, or the conjugate version phase noise. So you can still have some bias, which is not infinitely biased, but still has a lot more structure than just depolarizing noise. So for instance, highly Z biased noise, which will be the main topic of this talk, has PZ being much, much larger than either PX or PY. So I'm going to we're going to start very gently. We're going to introduce the repetition code, which is used in the classical setting to tackle bit flip noise. So we imagine that we want to transmit or compute one of two messages, just 1 or 0 message. We encode it into a bit string by repeating the symbol several times, for example, 3 times. And then when the receiver reads the message, say at the end of the computation or the end of a communication scenario, they just majority vote over the symbols that they see and output that as the received message. So if we have some noise that affects the qubits, so for example, the first, second, or third qubit are flipped from the intended symbol, then a majority voting will just reveal the original message and we've succeeded. But if we have more failures than successful bits, so 2 failures and 1 successfully transmitted bit, then we would decode this as 0, which is a failure. So to kind of transition to talking about quantum error correction, it's useful to think about the parity of the kind of parity constraints on the transmittable messages. So we look at both the transmittable messages or code words for the repetition code. We see that if we look at the last 2 bits of either of the 2 code words, they both have an even number of 1s. This has 2 1s and this has 2 0s. So there's a parity constraint on the transmittable code, the code words of the code. Similarly, if we look at the first 2 bits, they also have an even number of 1s. So to map this repetition code to the quantum setting, we know that, say, the 1 state is mapped to 1 1 1, 0 state is mapped to 0 0 0. And by the linearity of quantum mechanics, that means that if we want to encode some amount of 0 and some amount of 1, some superposition, we'll end up with a superposition of these 2 code words. And also, this parity constraint that we had earlier is still respected on both of these code words. So we know there's an even parity on the first 2 bits. And therefore, it's an eigenstate of the Z tensor Z tensor identity operator, where Z is just the Pauli Z operator. And the same for the last 2 bits. So we can check to see whether we have a code word of this particular code by just measuring these Pauli operators. So here's a circuit for doing that. We have our data qubits, which correspond to the 3 qubits that are actually in this 3-qubit repetition code, and then some syndrome or ancilla qubit that we're going to use to extract this syndrome information. So to extract the Z tensor identity information, we prepare the syndrome qubit in plus, do a pair of control NOT gates, and measure in the X basis. And similarly, we do the same thing down here for identity tensor Z. Okay, so that's the repetition code, but what we're going to talk about when I talk about the repetition code mostly throughout this talk is a conjugate version of it, where we basically write down the same code, but using eigenstates of the X operator. So the state is the code words are eigenstates of X tensor X. And to measure this observable, we basically do something very similar, but just do a control NOT gate instead of a control Z gate. And in the paper and throughout this talk, we're going to graphically represent this in a kind of 2D layout with this notation here. So the yellow qubits are always data qubits, and the gray qubits are the syndrome qubits. So to measure X tensor X, we'll represent that with half a circle to signify that this ancilla qubit is being used to measure X tensor X. And these other qubits are just surrounding things in the 2D layout. Okay, so that all tells us how we can just use a classical code to basically tackle infinitely biased noise. If you've heard about quantum error correction, you've almost certainly heard about the surface codes. The surface code is one of the best codes we know of for tackling depolarizing noise. And when we want to tackle depolarizing noise, we have to detect both X and Z errors. So we can't just measure one type of check. We have to measure checks made of Zs and Xs. And one way of doing that is by using this kind of square tiling here. So the half circles are still kind of X tensor X or Z tensor Z for blue, and X tensor X for red. But inside the bulk, away from the boundary, we have 4 qubit measurements. So to measure this check here, we would do control not, control not, control not, control not, and measure the ancilla. And here we see that the checks have to be weight 4 instead of weight 2 in the bulk because of commutativity. So this check here has to commute with the one adjacent to it, and to commute, they have to share an even number of qubits in common. And so that can be achieved with this particular layout. So the surface code is great. It protects against generic noise, but to protect against, order D errors, it needs order D squared data qubits because it has this square layout. Whereas if we just go back to the repetition code, if we imagine D of these in a line, you only need D qubits to protect against D over 2 bit flip errors. So it's kind of quadratically more expensive. If you were only protecting against 100 phase flip errors and no bit flips, and then suddenly you have to worry about both, then you have to deal with 10,000 data qubits. Okay, so if the noise is not infinitely biased, but a bit biased, we could, for example, use the thin surface code. So this is just one where the height and the width are asymmetrically distributed. And you can see that roughly the right ratio for this is going to be determined by the relative probabilities PZ and PX. Other alternatives to the thin surface code are available. So there's a lot of interesting work, especially recent work on kind of what you might call slight variants of the surface code that are useful for tackling bias noise, notably the XZZX surface code that doesn't just measure checks that are built of just X or just Z operators, but it's kind of mixed check. And then also the tailored surface codes that if you want to say measure, if you want to protect against phase noise, you would measure a mixture of checks made up of X, 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 and Y, 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 Y checks, and more. But we don't have time to cover these in this presentation. In the paper, we only talk about the thin surface code for various reasons. So the next important concept in understanding noise bias is understanding what a bias preserving gate is. So let's say that we're interested in Z bias. We've developed our code, say a thin surface code or repetition code, to tackle lots of Z errors, but not very many or any X errors. And what we don't want is that we're implementing unitaries that conjugate Z errors into X errors, because that completely eliminates any of the protection we get from our error correction code. So if we think about the C0 gate, this is safe because if we take a single Z error on the target and we conjugate it through, we get Z tensor Z. So, it hasn't created any X errors. And a single Z on the control will also just commute through. And so that's also safe. And so while that's okay for the full C0 gate, actually there are some severe problems with implementing the C0 gate in a standard qubit. So let's say that we want to implement a C0 gate in a 2-level system. So we've got our qubit and we're imagining that we always stay within the qubit subspace. We never excite out to some other level structure outside the qubit. Then there's a theorem in this paper that shows that you can't do that. And basically the idea is that, so you can't do it physically, right? You can't do the following. You can't have some time-dependent Hamiltonian that when you integrate over it, gives you the C0 gate without it being that there's some time in the middle of the C0 gate that if you inject a Z error at that point and conjugate it through this kind of partial C0 that you performed, you will always, so you'll always be able to find some time that when you try to do that, you'll find that there's some kind of X error, so it's not bias preserving. So you can't do it just using 2 levels, but you can do it using more than 2 levels. And in particular, we're going to be talking about implementing bias preserving gates using bosonic systems, so infinite dimensional systems. Okay, so that brings us to herding cats. So making qubits which are noise biased. And for this section of the talk, I'm going to apologize for the bad drawings, meow, which were partially a result of me getting a new tablet and deciding that I wanted to experiment with making slides that had some hand-drawn graphics in them with mixed levels of success. But after this section, we'll be back to pure, no hand drawings anymore. So here's the first of the bad hand drawings. So if we think about a simple harmonic oscillator, such as a pendulum, has a well-defined position and momentum. When we quantize the system, it no longer has a well-defined position or momentum. And the ground state, or the so-called vacuum state, if we look at it in the X basis, it has this simple Gaussian profile. So the simple harmonic oscillator has a kind of potential well that looks quadratic. And you have this ground state with some 0-point energy, and then equally spaced excited states going upwards that we typically think of as counting the number of excitations in the system, which are usually either photons or phonons. And many of the results that I will talk about today can be applicable to kind of phononic or photonic based cat qubits. So we have the annihilation operator that just moves us down this ladder of states by removing phonons or photons, and the creation operator that takes us up this ladder of states by just adding photons or phonons. Then the coherent state, which I'm sure any of you that have done an optics course have come across, it's basically laser light. The coherent state, alpha, where alpha can in general be any complex number, is a superposition of all these different kind of Fock states. If we look at it in the X basis, then at the coherent state, alpha is just a displaced version. So I've made a little mistake here. I displaced it to minus alpha instead of plus alpha. But anyway, you take this Gaussian envelope that describes the vacuum state, and you just displace it along the X coordinates when alpha is a real number. So yeah, when it's a complex number, it's less easy to see what's going on with respect to the wave function. And people normally plot it in terms of the Wigner function instead. So now I can say what the cat state is. So the even cat state is a equally weighted superposition of alpha and minus alpha. It has to have some kind of normalization factor here because these two states are not orthogonal. And I'll say more about that non-orthogonality later. So if we take two different states that are displaced by minus alpha and plus alpha and add them together, then we just have something that's a bimodal distribution with two peaks. So we also have that odd cat qubit, so called because actually if we ask how many photons this state contains, it would be an odd number. So the main difference here is that I put a minus sign instead of a plus sign, but also actually as a consequence, this normalization factor will also change. So you subtract these two states from each other and you'll get some other distribution that's now kind of zero at the origin. Okay, so what's the cat qubit? The cat qubit is any arbitrary superposition of the even and odd cat states. So we want to write down some psi, which is some mixture of zero logical and plus logical. So I have to define what I mean by the 0 and 1 logical basis states. So to define the 0 and 1 basis states for this encoding, we'll define it as follows. So an equally weighted plus superposition of 0 and 1 is equal to the even cat. And if I subtract 1 from 0 logical, I get the odd cat. And this entails what 0 and 1 are themselves. And you can check quite easily that 0 and 1 will be orthogonal as you like them to be. And what you can see is that they're kind of roughly going to be equal to alpha and minus alpha, right? So if I add these two lines together, I get the 0 logical state is going to be roughly equal to alpha. But because of the change in sign here, the minus alpha components will roughly cancel out. However, these two normalization constants aren't equal, and so they don't cancel out perfectly. So remember that I said that alpha and minus alpha are not exactly orthogonal. So they become, as you move these two peaks apart from each other, they become more and more orthogonal as you increase alpha. So you kind of exponentially make them more and more orthogonal. And if you write down what the 0 and 1 logical states are from just this previous slide, then what you find is that they're basically equal to alpha and minus alpha up to some correction that depends on the amount of non-orthogonality. So something that's exponentially suppressed in the size of alpha squared. Okay, so why are these qubits noise biased? Well, they're noise biased because the dominant noise source in any kind of bosonic system is almost always some form of loss, which we can think of as an application of the annihilation operator. And we know that the coherent state, alpha, is an eigenstate of the annihilation operator. So you just bring a scalar factor alpha outside the front. So what this means is that if we think about how the annihilation operator acts on a subspace spanned by alpha and minus alpha, it's never going to flip us between these two states. It can bring some number outside the front, which might have a phase and therefore lead to dephasing, but it's never going to flip between these two states. And since the 0 logical and the 1 logical state are equal to these two coherent states, also 0 logical and 1 logical are not flipped between by the process of loss. However, this is only approximately true up to this correction. And so what we have is that bit flips are exponentially suppressed in alpha squared, they should probably say. As you make alpha squared larger, you do actually increase the rate of Z errors because you can see that there's some kind of extra factor that crops up here, some extra scalar that grows with the size of alpha. You can make that more rigorous. Okay, so this isn't just a theorist dream. This is something which has already been experimentally observed in this paper by Les Kahn et al. So I've just pulled one of the key figures here from the archive version. So this is experimental data, and they're plotting the photon number, alpha squared, against the bit flip lifetime. And so this is on a log scale. And so what that means is that you can see that as you increase alpha squared, you're exponentially increasing the bit flip lifetime, which you can also think of as meaning that you're exponentially suppressing the probability of a bit flip. This is only true up to some kind of plateau where other physics takes over. And here this takes place at about alpha squared equals to 3. But that's, I mean, we believe that's due to certain features of their experimental setup that one could deal with, basically. And the alpha squared could probably be pushed up to something like 8. Okay, so how do we do gates? Well, the X gate is the simplest one to think about. It's just done adiabatically. So we think about these two different alpha and minus alpha states. If we move them around in phase space, like I'm illustrating here, slowly enough that you kind of, the alpha state always stays in the alpha state, then you'll perform an X gate. It's a bit harder to draw it in such a simple way. What happens if you want to do a C0 or a Toffoli gate? But C0 and Toffoli gates are kind of the same thing, right? They both permute the computational basis states. And so there will be some kind of adiabatic way of permuting the 2-qubit and 3-qubit computational basis states through phase space to implement the correct gate. And all of these cases, again, the same assumption, the same thing holds, right? That all of this is true up to some error that's exponentially suppressed in the size of alpha. Okay, so how do we make these qubits? I keep talking about cat qubits as if they're already prepared. And also, you know, there aren't just the 2 cat qubits. There's a whole level structure of infinite number of states that we don't want to be in for any of these things to be true. And in the paper, we talk about dissipative cats, although there are other approaches such as Kerr cats. And so for a dissipative system, it's useful to use this kind of jump operator notation. So I'm going to use D of some jump operator L, rho, to denote, you know, this particular process here. And then it's well known that if you just have a single such jump operator, the time derivative of rho with respect to t follows this simple differential equation, where kappa is the rate of this particular process. Now, if you have multiple jump operators, or you also have some Hamiltonian, which you would represent as just a commutator on the right-hand side, you can just add all these effects together, and that will give you an equation for how you time evolve rho. Okay, so if we imagine putting a jump operator in, which was just the annihilation operator, then we would see that the ground state is a fixed point of the dynamics, because if you apply the jump operator to the ground state, you get 0, so there'd be no time evolution. So if you're in the ground state, you wouldn't leave it if the only jump operator was the annihilation operator. But also for this particular jump operator, we know that all of the excited states would eventually relax down to the vacuum. So that gives us some idea of how to use dissipation to stabilize us or cool us and keep us in some particular state. Okay, so now we want to find some jump operator that stabilizes both the alpha and the minus alpha state. So we want some operator that, when we apply it to these states, gives 0. And this is achieved by just the annihilation squared minus alpha squared operator. And if you already know, remember the basic fact that the annihilation operator applied to some coherent state just brings the value of that coherence states, the plus or minus alpha as a scalar outside the front. Then you see that when you apply the annihilation operator squared, you're going to get plus or minus alpha all squared. And then because you're squaring it, the plus or minus sign doesn't matter. So you just get alpha squared and then the state back. So bringing the right-hand side of this equation over to the left-hand side, you see that a squared minus alpha squared applied to either the plus or minus alpha states gives us 0. And therefore, everything in the cat manifold is stabilized by this jump operator. And then it's a little bit more work to see that all of the states that are outside the manifold must eventually relax, because this is the only fixed point of this particular jump operator. Okay, so this is a 2-photon process because it involves the annihilation operator squared. So we're going to use kappa 2 to denote the rate of this particular process. But we will also have some loss processes that involve single photons. So the jump operator is just the annihilation operator example. So we'll denote those by kappa 1. Then what one finds is that the Z noise is largely determined by the ratio of these two processes, the good dissipation versus the bad dissipation. Okay, so a large part of the paper is kind of very quickly summarized in this one particular slide, which is that we did some extensive numerical simulations and also some perturbation theory analysis that involve several different things, looking at very rare events, very rare bit flip events. So, you know, we want to confirm that certain processes are only happening with probabilities that are all the way down to, say, 10 to the minus 10. We want to understand the non-adiabaticity effects in the control knot and the Toffoli gates. And we also want to understand crosstalk, where we have many qubits that are all coupled via some nonlinear element. And I guess one of the conclusions about crosstalk that I just want to very quickly summarize is that crosstalk we saw got very, very bad when we had more than 4 qubits coupled to the same nonlinear element. And so we don't want more than 4 or 5. Okay, so this is a very quick summary of many results. And I guess a technical point to make is that if you just try and do simulations of this kind using the Fock basis, what you'll see is that whenever you truncate, you're basically going to be cutting off something that's of order much bigger than 10 to the minus 10. So the truncation error will be too large. So what we used instead was the shifted Fock basis, where we take a bunch of, say, Fock states like 0, 1, 2, 3, 4, and shift them to plus alpha, but then also take the same set, shift it to minus alpha. So you'll definitely, with no approximation error, be able to describe the cat manifold, but also the few excited states outside it. The issue with using this basis is that it's not an orthogonal basis. So you have to be very, very careful on how you do things. But it gives us sufficiently small truncation error to be confident that we're seeing things at this level of precision. So I realize I'm saying going over this very quickly, and it is partly because I'm just giving you an overview talk. If you want to learn more about this very specific point of the paper, I really recommend that you can go watch this video that's available on YouTube by Kang Juno from the AWS team. So he talks specifically about cat qubit physics and the shifted Fock basis. So let me give a little highlight of some of the results in the paper, which is that if we just look at, let's say, the control knot gate, and we'll ignore some other things that we do study in the paper for simplicity, including dephasing noise and thermal noise, and just look at the effect of loss. And we'll keep alpha capped to no more than, say, 8 or 10, because some other weird nonlinear effects kick in past there. So what we can show is, what we found numerically is that all these different types of Pauli operators roughly have these probabilities of occurring over the course of a CNOT gate if you optimize the duration of the CNOT gate in the right way. So remember, kappa 1 over kappa 2 is this ratio of good noise versus bad noise. Let's pick some numbers which are ones that are used in some of the conclusions of the paper. So alpha squared equals 8, kappa 1 over kappa 2 is 10 to the minus 5. So all these numbers are quite aggressive and optimistic and quite far advanced from what was demonstrated in the Les Can paper. But at the same time, it kind of what we believe is possible with hard work. And then I would guess I would also conversely say that one of the conclusions that we'll come to later is this is kind of the ballpark region that you need to be in if you want your error correction code to have good performance. Okay, so what we see is that you have some Z noise, which is of order like 10 to the minus 2 or 10 to the minus 3, but then bit flip Floyd noise is really, really low down into the 10 to the minus 10, 10 to the minus 13 territory. So you do have this extreme noise bias for this system. That's what we believe. Okay, so let's abstract away some of the details. In some subsequent slides, we're going to use this kind of layout notation. So data qubits, syndrome qubits, and then a tile. So remember I said that crosstalk means that you can't couple more than 4 or 5 qubits together. So a square represents qubits that can be coupled together. And we assume that you can perform a CNOT gate between any pair that share a tile and a Toffoli gate between any triple that share a tile. And also that these gates, the CNOT and Toffoli gates, are adiabatically performed and are bias preserving so that they keep the bit flip errors exponentially suppressed. Okay, so what are the results on error correction that we have? So I've made a lot of slides, so hopefully I'll get through in good enough time, but please give me a time warning if I need to speed up dramatically. So I've already introduced the repetition code, and this is how it looks in our layout, and hopefully what each of these elements are is a bit clearer now. Each one is a cat qubit. Okay, so let's plug in the kappa ratio that I was talking about on the previous slide, and let's simulate the process of error correction using exactly the noise model that's been derived based on the physics of the system. And then let's look at the combination of X and Z logical errors for this repetition code as a function of the size of the repetition code. So what we'll see is that as we make the repetition code larger, we're exponentially suppressing phase errors. So we have an exponential drop in the logical error rate, but we're not doing anything about bit flip errors. And so the bit flip errors are coming from a very, very low level, linearly increasing with the size of the code, because as we add more qubits, there's more locations for bit flip to happen. And what we see is that for this particular set of parameters, as an example, and we give, there's a minima at 9 qubits. So we can get all the way down to say 10 to the minus 8, well, a bit more than 10 to the minus 8 logical error rate. So throughout this talk, I'm really just picking out very specific examples. And if you go to the paper, for example, there's a plot that looks like this with 3 different curves on it, but I'm trying to strip it down to the bare minima just to communicate some key points, key messages from the paper. So I think a key message that I take away from this is that such an architecture with a repetition code would be good enough for algorithms that had a depth that was thousands of gates. So you can look at 10 to the minus 8 and think, well, that's much, I should be able to do more than 1,000 gates, but you have to think about depth times width. So if you have 100 logical qubits and 1,000 gates deep, then you're going to need the logical error rates per each one of those potential fault sites to be much, much less than, let's say, 10 to the minus 7. So that's the most that you can hope for. It's going to be enough that you could do something that there's no known way how to simulate if you said had 1,000 Toffoli gates and 100 logical qubits. But there aren't any algorithms that we know of, outside of the NISQ type setting. I'm talking about a fault-tolerant setting now, where it's strongly believed that that would be enough gates to demonstrate something that had really solid quantum advantage. So, I think I guess I cited this paper by Goulard and Mirahimi earlier, and I should probably say that that paper proposed the idea of using cat qubits concatenated with repetition codes. And it's a starting point for a lot of the analysis that we did. But I think one of the conclusions that I take away from this work personally is that to make such an architecture work for an algorithm where we think there's quantum advantage, you need to do something fundamentally different from what's been proposed already, or you just have to modify it and work with the cat qubit concatenated with something else, such as the thin surface code. So here is a thin surface code with dx distance 3, which means it can tolerate a single bit flip error. The repetition code couldn't handle any, this can handle 1. So one of the things, so we did lots of simulations just for this particular choice of dx. And what we found, so we did it for memory errors, we did it for time-like errors. And what we found is that this would be enough if you wanted an algorithm that had a depth that was of order millions of gates. So then you start reaching a territory where you can talk about having quantum advantage over classical computing. If you wanted to solve, there are some bigger problems, for example, solving for MoCA, where even dx equals 3 would not be enough. I'd have to go to something like dx equals 5 or 7. Okay, so that tells us how memory works in this particular architecture. So how do we do computation? So on the previous slide, kind of had one of these pictures here where I mentioned that we simulated time-like errors. And this kind of picture here is meant to denote memory of the system. So you've got a time direction, just storing 2 qubits not interacting at all. And then you can kind of do this thing where in the time direction, they get merged into one code block for a while. And this is a process known as lattice surgery. So lattice surgery suffices to measure logical Pauli operators between different blocks of surface codes. And from that, you know, you can also perform any kind of Clifford operations. This includes things like control not gates, Hadamard gates. All of these things can be done at the logical level using some lattice surgery or variant trick. But you can't use lattice surgery to do non-Clifford gates, at least without some kind of extra element. So the key question is, how do you implement something else? Like the T gate is the thing that most people talk about, but Toffoli will also give you a universal gate set when combined with the Clifford gate. So in our paper, we talk about doing the Toffoli gate at the physical level in a way that's adiabatic, but at the logical level, we want to prepare something called the Toffoli state. So the Toffoli state is a 3-qubit state that looks like this. I suppose a way to see why it's the Toffoli state. Well, I get an interesting piece of trivia about it is that if you take the first 2 bits and compute the AND of them, you get the value of the 3rd bit. And that's related to the fact that the Toffoli gate, what it does is it takes the AND of the first 2 bits and adds it to the 3rd bit. So an interesting observation that we make about the Toffoli state is that it can be described in terms of a set of Cliffords. So there's 3 Cliffords that stabilize the Toffoli. So we apply them to the Toffoli and we get the Toffoli back. And these Cliffords are, for example, XA, and then the C not acting on qubits B and C. So here we're labeling the qubits by A, B, and C. Similarly for GB, we have some mixture of bit flip and C not. The 3rd one is kind of a little bit different because the 3rd qubit is different in the Toffoli state. It has a Z and a control Z gate instead. So, I mean, I guess many people will be familiar with the idea of representing a quantum state that is, for example, a stabilizer state by a set of Pauli operators that the state is a unique eigenstate of. And what we find is that for magic states, such as the Toffoli state, it's the unique eigenstate of some set of Clifford operators. So what that tells us is that if we could measure these Clifford operators and somehow be confident that we got the +1 outcome, then we would know that we were in the Toffoli state. Furthermore, once we've got the Toffoli state, we can implement the Toffoli gate using just no Clifford procedures, right? So we can take the Toffoli state, some arbitrary logical state. So I'm imagining that each one of these lines here is a logical qubit, so a cat qubit concatenated with, say, a repetition code or a surface code. You do some C0 gates pointing in some direction, you measure some single qubit logical operator, and then you have to do some correction. But at the end of it, you end up with a Toffoli gate. So to implement a high fidelity Toffoli state, the full picture that we present, if you want to do something that has a high enough fidelity for the purpose of, say, 1 million Toffoli gate algorithm, is at the physical level, we use this cat qubit adiabatic Toffoli. Then we use a protocol, which I'm going to spend a bit of time telling you about over the next few slides, called the bottom-up Toffoli. And this repairs Toffoli states using a repetition code, and it improves the fidelity beyond what you get with the adiabatic Toffoli. But it doesn't get it, we can't push it as far as we really need to. And so there's a 3rd thing that goes in the mix that I'm going to spend less time talking about because it's quite technical and I expect I'll run out of time. And this is called top-down Toffoli, which is a protocol that takes the higher fidelity Toffoli states out of bottom of Toffoli and then uses a novel magic state factory construction and a mixture of surface and repetition codes that did it further. I'll say a little bit about that. Okay. Right, so on to bottom-up Toffoli. So I think there are 3 kind of key insights that go into the design of the bottom-up Toffoli procedure. So the first one is that if we take one of these things, which is a stable, which stabilize the Toffoli state, say the GA operator, what we note is that it's transversal for any CSS code. So I haven't defined CSS, but it just means any quantum error correction code that's built up of checks that are just ZZZ type or XXXX type. So repetition code, surface code, they always have this as a transversal gate, which means that if I apply these gates bitwise to each of the qubits, then I'll get the logical gate. The second insight is that if I add a control to this, so I think about the control GA gate, then that can be performed using a C0 and a Toffoli gate, because I'll have control X is C0 and control not is simply the Toffoli gate. And the third insight that goes into the mix is that physical errors on an unencoded ancilla just lead to flipped measurement outcomes. And so to deal with physical errors, so Z errors, okay, so when I say physical errors here, I'm assuming that we have this Z noise bias, right? So physical errors, which are Z errors on unencoded ancillas, just lead to flipped measurement outcomes. So we've got this kind of sketch of the circuit here. We have this thing that repairs the psi1 state. Oh, hang on. Let me just see where psi1's, sorry, I've deleted the slide with psi1 defined on it. I'll have to tell you what psi1 is in a moment. Okay, so there's some state that you can prepare. And the interesting thing about this state is that it's already an eigenstate of GA and GC. So the only thing you need to do is measure GA, and it will project you down into the Toffoli state. So I think that's pretty cool, is this insight that there's like a 3-qubit state, and you only have to measure one observable to collapse it down to the Toffoli state. Okay, so to collapse it down to the Toffoli state, we need to measure GA. So we can do that by doing controlled GA using an ancilla that's just in the plus state. And let's say that there's a Z error anywhere here. So there's a Z error here, and it's just going to flip the outcome of the measurement that we get. So we can't trust the outcomes of these measurements. If there's a Z error here, it's going through a C0 gate, and the C0 gate is bias preserving. So it'll just propagate to some other combination of Z errors. So we're never going to have a problem that a Z error does anything other than propagate to Z errors or flip an outcome on one of these measurements. So these can't be trusted. So we just need to repeat several times. And these blue blocks just represent error correction done at, sorry, various points. So I think another key thing that differentiates our paper from some of the other work, including the paper that I mentioned earlier that proposed looking at CAT and repetition codes. So in that paper, they proposed a few different Toffoli schemes, but they never compiled them down to a 2D architecture. So one of the cool things about the bottom-up Toffoli protocol is, even though it looks, when I present it as a circuit like this, that like if I was to promote each one of these lines to say a repetition code, it's going to be really, it looks like it's going to be really, really hard to do it in a way that can be laid out in 2D without having to do lots of swap gates all the time, because this gate looks like a massively non-local gate. But actually there is a way to do it. And it just involves kind of having these 3 repetition codes here. This one kind of has the snake around the corner. And these here, so there was, if you remember on the previous slide, there's a plus state. So that has to interact with everything, which is not possible. So what we do instead is an equivalent thing, which is you replace the plus with a G8Z state. And so that's what this set of ancillas are prepared in here. So when we want to measure GA, you have to do a Toffoli gate. So you have to do a Toffoli here, a Toffoli here, a Toffoli here, a Toffoli here, and a Toffoli here. We have to do a controlled X gate. But X logical is a single qubit operator. So we can just do a single CX gate here. And that gives us all of the gates that we need for one of these particular blocks here. And we just have to repeat it several times. Okay, so again, we can do a full circuit level simulation of this protocol using the error model that has been built up from the ground in terms of simulating these systems and seeing what the noise will be like. And this is the result that we get for different distances that are used for the bottom-up Toffoli protocol as a function of the ratio of these 2 different 1 and 2 photon noise processes. And I guess the numbers that I've been highlighting throughout are for the 10⁻⁵ regime, so the lower end here. And what we can see is that you can get the Toffoli gate down to, say, 10⁻⁴ roughly, total Z error rate. So this is good because originally the error rate of a single Toffoli gate is going to be of order about 3%. So it's a massive reduction from 3% down to, roughly 10 to the minus 5, let's say. So again, I want to make this point that I was making earlier, that this is good enough for some purposes. If we just want to use the bottom-up Toffoli protocol, just with the repetition code, then you can see that if you wanted to use 1,000 of these Toffoli gates, it would contribute less than 1% to total algorithm failure. So this is really telling us again that we could hope to, with a very, very, very small footprint unit for implementing Toffoli gates, we could, say, implement 1,000 Toffoli gates in an algorithm. Okay, so here's the reference that I probably should have given you an earlier point in the talk. So these are the two papers, well, two of the papers in the literature that look at repetition. Yeah, okay, sorry, there's a second one here. I think I've repeated the same reference twice. They look at the repetition code concatenated with cat qubits, and they proposed a particular scheme for doing the Toffoli gate. So their construction was not 2D. It needed very high distance repetition codes to get high fidelity Toffoli gates. But as we've already seen, actually, you can't really push the distance of repetition code past 9 before before you go past this minima, right? There was an ideal minima beyond which the effect of increasing the code distance just made the bit flip noise worse, right? So the total logical error rate was getting worse as we made D bigger than 9. And to some extent in their analysis, they're kind of assuming that bit flips are negligible. So these are some of the points in which our Toffoli construction goes past the prior art. So yeah, the last thing that was kind of promised, or the penultimate thing actually, because I'll say a little bit about algorithms as well, is the top-down protocol. So this is a way of taking the output on bottom-up Toffoli and further distilling it. So it's a routine for taking Toffoli states and convert them to Toffoli states. And this is just a one-slide job because it would take many more slides to do it in detail, to do it justice. So, so you can see this is much more zoomed out here. Each one of these is a qubit. And this is a factory that will take 8 Toffoli states that are produced by one of these units that I've labeled BU for bottom-up, and converting 8 of these into 2 much higher fidelity Toffoli states. And you can see that the footprint of this thing, the amount of area that it covers, is significantly larger than it was for a single bottom-up Toffoli unit. So that's the sense in which bottom-up Toffoli has an extremely low footprint. But still, this factory design itself also has a very small footprint. And the reason for that is that, to get very good error rates, we know we're going to have to rely on surface code. So if you can see inside these yellow boxes here, there's a kind of, below the translucent white covering, there's a thin surface code. But these blocks here are just using the repetition code. So it's a factory that uses a hybrid of repetition code and surface code. And so if it was a factory that was just surface code everywhere, including in these kind of lower level blocks, it would be considerably larger. So yeah, this is a new protocol. There wasn't previously a design that took 8 Toffoli states to 2 Toffoli states. And again, it was analyzed using the noise model propagated all the way from the lowest level, all the way through how we understand the bottom of Toffoli protocol to operate, and then all the way through the operation of the top down. Okay, so the final wrapping up part of this talk is just a few slides now to go. It's just commenting on how this all adds up for some particular target problem. And we chose simulating the Hubbard model. So I'm not going to have time to discuss what the Hubbard model is. It's some condensed matter model that people believe might tell us something about superconductivity. And here's, so yeah, the paper. We don't talk about the Hubbard model algorithm directly in the paper. Those details are covered in a companion paper. So here's the reference. So this companion paper basically looks at if we made the lattice a certain size, how many logical qubits we need, and how many Toffoli gates we would need to simulate that particular size of the Hubbard model to achieve some particular precision estimate of the ground state energy. I should probably add there's also a paper by the Kivlichin et al. So the Google group paper that also looks at the Hubbard model and Jellium and other stuff. So to execute this, we need Toffoli gates and T gates. We can just use a catalysis trick to get T gates from Toffoli states. And then there's a kind of partner table in the architecture paper, right? So the Hubbard model paper, right, which is just me as an author, tells you about the complexity in terms of T gates and Toffoli gates. And then in the architecture paper, we convert this into a statement about what the runtime would be, taking into account how long it takes to execute each one of these control not gates and what the footprint is. So I'm using here a unit, which is number of ATSs, which you can think of as being a number of these square tiles that we had. What you'll notice is that, for example, the percentage of the system which is used by the factory is very, very small. And the headline number, so if you read the abstract of the paper, you'll see a statement about 32,000 units or building blocks being used to solve some particular problem. And that comes from this row in the table. So we're saying that if you have an 8x8 Hubbard model and you fix a certain ratio of the parameters, so this is like the ratio of the hopping strength versus the interaction strength to be 8, which is right bang in the middle where it's of the regime where it's believed to be hard to simulate this model. Then you need 32,000 of these elements, and the runtime would be about an hour. And so there are some assumptions that go into this, including like a 1.3 multiplier for matter surgery and routing costs. That's the only bit that I would say is a little bit hacky, but I think that it's accurate. Okay, yeah, and then one can also make a comparison with the other architectures, such as the superconducting transmon architecture. But I expect I'm running out of time, so someone can ask me about that if they're interested in more. Yeah, so the paper, I believe, is one of the very few papers that goes all the way from thinking about what parameters we could expect for a particular hardware, what noise model you would get from that, what the consequences would be for error correction, how that would propagate through magic state distillation, and then an application to an algorithm. So it really is kind of a full stack analysis in some sense. But of course, you know, there's a lot of work to be done to see if these parameters are actually achievable. And so, yeah, lots more work to do. Thank you for listening.
Okay. So if anybody has any questions, either they can raise their hand, virtual hand, or they can unmute and ask. So maybe I'll ask the first question. You mentioned before there was a difference between cats using dissipation and Kerr cats. Could you define the Kerr cat?
Yes. Pardon? Could
you define the Kerr cat, please?
Yeah, the Kerr cat. So imagine that you had no dissipation turned on. You could just, for example, write down a Hamiltonian where the ground state manifold of the Hamiltonian was basically the even and odd cat states, right? So, and then you could, in some sense, maybe hope that those states are energetically favored, and so you end up in these states if you just cool the system.
Mm-hmm.
So one of the advantages of the Kerr cat is that you don't have to worry about doing things quite. You can do the gates a lot faster.
Mm-hmm.
And it's believed that you can do the gates to higher fidelity in some sense, but there is a bit of an issue, which is that you will have a lot of leakage outside of the ground state manifold, and it's not clear how quickly you'll relax back down into the cat manifold. And one can also imagine like a combination of the two, right? So you have some Hamiltonian term that encourages you to be in the cat manifold, but you also have some dissipative mechanism that also removes excitations to keep you inside the cat manifold.
Mm-hmm. Okay. Okay, thank you. Any other questions for Professor Campbell? Okay, so it is...
Hello, I'm having trouble finding the raise hand thing. Hi, it's somewhere on one of these, the bottom. Anyway, never mind. So question, when you were defining these cat states and doing a bunch of the analysis, you were kind of saying alpha up to about 8, above which you get extra problems.
Yeah.
So is there an optimal alpha that you want to pick, or do you have some freedom in there? And does it matter that how accurately do you have to keep your alpha when you're making these?
I think the answer is that it matters, and it matters a lot.
Mm-hmm.
Yeah. So, you know, I was saying that there are lots of assumptions that kind of go into the analysis that assume that maybe alpha isn't too large, and I guess one can have that assume that alpha isn't too large. So maybe I can just say what one of those things is. So I kind of wrote down a dissipator as if it was just kind of given to us, but where did the dissipator come from, right? So in fact, what happens is that you have some Hamiltonian that involves the system and also a bath, and the bath is very, very lossy. And you design the Hamiltonian in such a way that kind of you move an excitation into the bath and it goes from the bath out of the system, right? And to get the dissipator from the kind of church of the larger Hilbert space dynamics, you have to do some adiabatic elimination. And this is only accurate in some particular parameter regime. And as you ramp alpha up, you start to leave the parameter regime where that's true anymore. So in fact, one of the things that you start to see is that the dynamics is no longer, I mean, first of all, it's hard to describe the dynamics using open system dynamics, but also you start to get some coherent effects. So the noise is no longer like a Pauli noise channel. So I think in this paper, we've argued that alpha squared equals to 8 should be reasonable, but we'll see, you know, if that's still the consensus in a few years' time or not.
Right. Yeah. One of my motivations for asking is because I was one of my other PhD students were looking at swap tests, and it was actually an undergraduate project, and we were looking at them for cat states and related kind of states, and you get something more interesting happening when alpha is order 1. And then it goes back to being what you'd expect above that. So
well, alpha equals 1.
Interesting, yes.
Yeah.
One
you don't have this the bit flip suppression. You can see that in this table here, they barely start at alpha squared equals to 1. So
yeah.
The two states, the alpha and the minus alpha state, have a very high overlap there. So this bit flip suppression is not going to be very prominent. So I was arguing for like alpha squared 8 somewhere over here, or maybe 6. You know, at one point we were talking about 10, but I think that's a bit too bullish.
Okay,
so, you know, 3 is achievable, right? Because it's already been done in an experiment, but there's numerous things that were not done in this experiment that would enable you to push up to much, much higher alpha squared. You know, this is kind of like a first prototype. So
yeah, so alpha squared is 3 is kind of 1.7 or thereabouts. For alpha, I'm thinking. I'm not.
Oh, for alpha. Oh, you're asking me to square root on the spot. Yeah. Okay. That sounds plausible.
Yeah. So an alpha squared is 8. You're 2 root 2. So you're 2.8.
Yeah.
Alpha is 3. So it's just above that sort of approximate single photon regime, but it definitely isn't in it, and that's because of the overlap, right? Yeah. Okay, got you. So that's the competing things. It's that orthogonality versus getting too high and too many photons in there.
Yeah, I mean, there's this other thing that I kind of briefly alluded to, which is that as you increase alpha, you suppress bit flips, which is tied into this orthogonality question. But you also increase the rate of phase flips linearly, right? So if you think about the effect of the annihilation operator, it kind of pulls a scalar outside the front of the state, which is of size alpha, right?
Yeah.
So, maybe it's more than linearly actually. But anyway, you get some scalar factor that depends on alpha, right? In the rate of the phase errors.
Yeah, yeah. There's a sweet spot, definitely, and we don't know exactly what it is because there's so many factors, right? Yeah.
Yeah, I mean, there's certainly a case actually for not pushing as hard in terms of high alpha as maybe we've been doing in this work, because if I come back to this table here, what you'll see is that you have a very, very large noise bias. So this was for alpha squared equal to 8. But phase errors are happening like with 3% probability, which is actually very, very high. When you think that the surface code, if you had depolarizing noise, has a threshold that's about 1%. If all of these were 3%, then it would not be below threshold. So you would not be able to do error correction at all. So this is almost like too high, right? And one could very well ask, you know, is it worth having this particular Pauli noise so high that it seems like almost above threshold in some sense to gain, you know, a massive reduction in these other error rates?
Yeah, you don't really want to be close to threshold, right? Because it increases
You
your
never
risk.
want to be close to threshold, but here you're playing the dephasing noise you're playing with very, very close to threshold. I mean, the threshold is higher because the other error rates are so much lower, right? So when you have an asymmetric, it's not like it's 1% for each one of them, but yeah, there's a complex trade-off.
Yeah. Cool. Thank you.
Okay, so maybe let's thank Professor Campbell one more time.
Thank you. Thanks for the invitation. Oh, there you are, Viv, over there. I'll put you on the other screen. Hello.
Oh, yeah.